We are now in section 7.1, which I'm new to chapter 7. We're going to talk about exponential functions, their graphs, and some applications today. So in general, an exponential function is going to be a function, so we have f of x, in which your independent variable x is in the exponent. It's in the exponent. So, oh, there it is, exponent. So in our exponential functions, we have a base, and then that is to a variable x. The base cannot be 0 or 1. In the domain, we have no restrictions. The domain is all real numbers. However, the range will only be positive numbers, not even 0, but you will only get out positive numbers, even when x is negative. A number raised to a power will always give you a positive number. Okay, so in the graph, there are two special features that you have to know. One is the y-intercept, and that is at 1, it's the point 0, 1. And the other is the horizontal asymptote, which is the x-axis. Okay, so you need to know the two graphs, or the graphs. There's really only one graph. I'll explain why the second graph is just a transformation of the first graph in a second. So y equals a to the x. This works for any base that's greater than 1. By the way, our bases are never going to be negative either. They're only going to be fractions between 0 and 1, or numbers larger than 1. Okay, and so you can see why if x equals 0, y equals a to the 0, a to the 0 is 1. And that's our y-intercept 0, 1. So these are those two features that I want you to know. And then the graph looks like this. This is an exponential growth graph. And so this horizontal asymptote, y equals 0, is actually only on the left end. And then you explode up to infinity on the right side. Okay, in the other case, this is called exponential decay. But when your a is a fraction between 0 and 1, you're actually dividing by, that means that a can be written as 1 over some other number. And so it's a fraction, and you ended up dividing by that fraction every single time. You have the same kind of features, the horizontal asymptote at 0 and the y-intercept at 1, but this is decay instead of growth. And so instead of at the left end, when x is negative infinity, getting 0, now you have the horizontal asymptote at the right side. Another way of thinking about this is if a is a fraction and a equals b to the is 1 over b, and that means that a to the negative 1 or b to the negative 1 is a. And so think about that as b to the, or a, it doesn't matter, to the negative 1, that's raised to the x. So that's why equals a to the negative x. If a is a positive number, that is larger than 1. And so you can see this is just the reflection over the line, or over the y-axis. Reflection over the x, y, that's the y-axis. Okay, and that's what happens when you replace, this is the same as y equals a to the negative x if a is more than 1. And that's what happens if you stick a negative in front of the x, you reflect over the y-axis. Okay. I'd like you to take a moment and see how many of these 7 exponent rules you can remember. So go ahead and pause the video and write down as many rules as you can remember. I'm going to check these tomorrow. Okay, so we're going to graph exponential functions, and then with whenever we have graphing, we worry about transformations. So in this first example, I have y equals 4 to the x. It does not matter what the base is, so long as the base is larger than 1. So I'm going to graph the same picture for 4 to the x as I graph for 2 to the x. Technically, there are some differences there, but the differences are somewhat minor. Okay, so that means exponential growth. So this is f, 4 to the x. So now let's graph g. What is g going to do? Well, I have a negative here, so this is going to reflect over the x-axis. And then I have a plus 2 in beside the x. This is not a plus 2 at the end. We don't have negative 4 to the x plus 2 at the end. We have plus 2 up here inside with the x. So that means I'm going to go left 2. So I'm going to reflect over the x-axis and go left 2. So let me reflect over the x-axis first. That would give me the point 0, negative 1. And then left 2 means this is now going to be negative 2, 0. And that horizontal asymptote won't change. But I will cross at a different y value. Okay. And sometimes it's better to sketch the graph without doing transformations. And so I'm going to sketch the graph over here, and I'm going to come up with a table of values over here. Either way is fine. So we want to do x equals 0. When x is 0, y is going to be 3 to the 2 minus 1. That's 8. So I have 0, 8. And then let's do negative 1 next. Because that's going to give me 3 to the positive 1 minus 1, which is 2. And let's see here. Let's do negative 2 next. This is where I get that 3 to the 0, which is 1 minus 1, so 0. And then can I use negative 3? What would happen at negative 3? Well, at negative 3, I would get 3 to the negative 1. That's a negative 1 minus 1. So that's 1/3 minus 1. That's negative 2/3. So at negative 3, I have negative 2/3. So I'm getting a fraction now. All right, let's try. And I already did x equals 0, right? Okay. So what's happening here is I have my normal 3 to the x graph. This is going to shift me down 1. That means my horizontal asymptote is here at y equals negative 1. So even if you plot points, you still have to look for that horizontal asymptote. If you weren't sure about it, you could have also plugged in negative 4. At negative 4, you're going to get 1/9 minus 1. That's negative 8/9. So you're getting closer and closer to 1. And then I'm going to sketch my graph. And that's a nice graph there with all those points on it. Okay. So that was just a brief introduction into exponential functions, and you've had work with exponential functions before. We're going to talk for the rest of the time about applications of exponential functions, and this is growth and decay. So the two we study, we're going to study two. The first one is money and compound interest. So if you have an account somewhere in which you are either earning interest or maybe you have a debt and you're paying interest, then the balance is the amount that you either owe or have in the bank, and that's A. P is the principal. That would be the original loan amount, or the amount that you owe on the loan. Yeah, that would be the original loan amount. And then, or the original investment amount. And then R is your interest rate. Remember that if your R is 6%, that percent means divided by 100. So notice I'm not just randomly dropping a percent symbol. I am converting it into its mathematical operation of divided by 100, and that is 0.06. So whenever you put R in, it's not the number 6 if your interest rate is 6%. It's the number 6%, which is 6 per 100, which is 6 divided by 100. Okay, and that is this formula. This formula is when, okay, interrupted. So when you are compounded, when you have money invested, then the amount in the account changes as time changes because of the interest that you either accrue or pay. Okay, so N is something that happens most often, and that's the number of times that the investment is compounded. So for example, mortgages are compounded, it's called monthly. So when a mortgage is compounded monthly, every month the bank will calculate the amount of interest that you owe on the loan for that portion of the loan, or that portion of the year, because your interest rate is an annual interest rate. And so you take that annual interest rate and you divide it up among your 12 payments for the year, and then you take that times the amount. So it goes in there like that. So that's when you're compounded n times a year. And I can go over that in more detail later. Compounded continuously is means that it's calculated instantaneously. The amount, like the interest that you are due, is instantaneously put into your account. And that follows this different formula, which is A equals PEGRT. All right, and then you have the other application that we're going to focus on is radioactive decay. And radioactive decay is when radioactive isotopes will sporadically become, like half of them will regenerate into a different form, like with carbon, the C12 will change to C14 after you die, and that takes like 5,700 and some years for exactly half of it to decay. And so if, like in the example of carbon, your half-life then would be 5,700 and I think it's 30. But this will be given in the problem, and if not, that'll be the question. T is the amount of time that has elapsed, and your base number is 1/2, and that's because you get half as much as you originally had. P is your initial amount, your principal of, say, carbon 12, and then your amount is the amount that you have as a function of T at that time later. Okay, so we're going to do 3 examples. Our first example is a half-life one. So I'm going to write down A equals P 1/2 to the T over H. So it says that a certain radioactive isotope has a half-life of 37 years. How long for 100 grams to decay to 64 grams? So that would mean that I initially had 100 grams. I'm figuring out the amount of time it has taken, and my half-life is 37, and the amount of time it takes to get to 64, for my amount to be 64. And now I'm going to solve this equation. I want you to be very careful about how you solve for T here. Okay, there are lots of numbers. There's a 100, there's a base 1/2, and there's a divided by 37. All that you need to get rid of all of these until you eventually have a T equals, which is the goal, right? T equals this. But in order to do that, we're gonna do some reverse operations on these numbers until we have just a T. So which number do you get rid of first? Be very careful. This 100 is not allowed to multiply to the 1/2. No, because order of operations says you do the exponents before you multiply. And so the very first thing that you do is you divide by 100. So the very first step is divide both sides of the equation by 100. And so I get 0.64 equals 1/2 to the T over 37. Now the next thing to do is to get rid of this base 1/2. And that involves doing an inverse exponent. We're inverting the exponent. We don't want an exponent anymore. And so that's called a logarithm. And we will focus more on those later. For right now, I just want you to know that you do a log base 1/2 of 0.64. And that will equal T over 37. So I eliminate the base 1/2 here by making it a base 1/2 of a logarithm on the opposite side. And then the last thing to do is multiply by 37. Okay, and then you have to type that into your calculator. All right, so here's my calculator, and I am doing the log. So I hit Control, Log, and on the Inspires, you have a choice. You can put in base 1/2. And that's what I'm going to type in, the base 1/2. And then I was doing the logarithm of 0.64, and then I had to multiply that by 37. And so my answer is 23.823. 23.823 years is the amount of time it takes. Okay, I'm going to leave, let's do this one. Well, yeah, Let's do this one. Okay, example 2. I again have a radioactive isotope. So A equals P 1/2 to the T over H. So I have a half-life of 14 years. 19 grams are left after 5 years. So when T is 5, A is 19. The question is, how much was present initially? How much was present initially? All right, well, P is multiplied by this number, which you can calculate. And then I need to take 19 divided by that. 1/2 to the 5/14. And then that will be P. So I'm just dividing both sides by that number. So over here on my calculator, 19 divided by 1/2. Let me put that in parentheses. To the, and then the exponent was 5/14. Okay, and I'm going to hit Control Enter to get the decimal. So that's 24.337. 24.337. Right. Is that the unit? Yes. And that makes sense because notice a full half-life hasn't gone. So I didn't get half of 25, or I didn't get double 19. All right, last question is our compounding question. We have how much time is required for an investment to double if you earn 6.25% compounded monthly versus continuously. Monthly, compounding monthly, means that n equals 12. Compounding continuously means I use PERT, A equals PE to the RT. Monthly means I use A equals P 1 plus R over N to the NT. Okay, so doubling. Notice I don't know the initial investment. It turns out that it does not matter what the initial investment was. The time it takes to double is dependent only upon how it's compounded and the interest rate. But if that confuses you, just assume that your initial investment is $100. That always works. Always works. So in the case of monthly, I have 200 equals 100 because I'm doubling. 1 plus 6.25% divided by 12 to the 12t. And I have to figure out the amount of time that takes. And then this next step is the reason why it doesn't matter whether you start with $100 or a penny. And that's because your first step is to divide by the initial amount. And if you doubled your initial amount, anytime you divide A by that, you get 2. 1 plus 0.0625 over 12 to the 12t. Now I have to eliminate the base. That means I have to put it as a base of a logarithm. I'm being very careful not to round. You have to be very careful not to round. So my base is this strange number, the log of 2 with this strange base. And that equals 12t. And so I'm going to take that and divide by 12. So here's my calculator. I'm going to do the log base 1 plus 0.0625 divided by 12. Notice how I don't round anything of 2. And then that gets times by 12. Oh no, it got divided by 12, didn't it? I'm going to copy that down and change this times to a divide. Yes. And so then the time it takes to double is 11.119 years. So T equals 11.119 years. Okay, and then I'm going to leave you to do this last one on your own. It's again the same question. The interest rate is 6.25%, and you're solving for the time it takes to double. I'll give you a hint. The answer is close to 11, but it's less. And that is all. Oh my